We created a bubble ring simulation based on an interesting paper we found. This problem of rendering and simulating a bubble ring shows that fascinating natural phenomena can be simplified on a computer effectively. Our starting point was the Project 4 starter code and code from the paper for the Houdini physics simulator.
Here's a quick demo of our bubble ring simulation, in which our bubble ring starts with a tilt of 45 degrees across the z-axis. And as you can see, the bubble is expanding while its thickness is actually decreasing. And this is due to the forces of gravity and buoyancy, as well as a fluid dynamics differential equation.
For the simulation, we look to understand and implement the physics in Python, referencing the physics described in the paper and their Houdini code. Here is the physics pipeline to simulate the bubble ring.
In the Project 4 code, the simulation logic is all contained within the simulate function. We successfully implemented everything here in blue and C++ to combine with the rendering. We use the Runge-Kutta fourth order integration method to update the positions and thicknesses.
Further, resampling maintains numerical stability, thickness flow controls the distribution of air within the bubble, and reconnection merges colliding bubbles. These components unfortunately did not make it into the C++ simulation, however, are implemented in Python, shown here in this very cool two-ring collision.
For the C++ simulation, our starting point was Project 4 CloudSim because it was already able to render and simulate wireframes. We first meshed the outside of the bubble ring. The diagram in the bottom left illustrates how we did that, showing the meshing process for one segment of the bubble ring.
To shade the bubble ring, we used a cube map version of water caustics as the environment, which lets us simulate the appearance of reflective ripples on the bubble ring surface.
In conclusion, interactions between bubble rings are complex and beautiful and carry a lot of potential for simulation and rendering. One thing we learned is that by implementing first in Python, we got a working model without having to deal with C++ debugging. And we were also able to effectively parallelize our work between the physics and rendering teams. Thank you.